Hello students, so in this lecture we will discuss about defects, especially occurring in nanomaterials. Now defects, we know about different types of defects like linear defects, point defects, planar defects, but let's talk about planar defects because it will be important in the case of nanomaterials. Now, by planar defects, we mean twins, which are the crystallographic mirror images, and stacking faults. It means ABC, ABC. If this is how the stacking faults look like, you suddenly get a layer which has got a different orientation than the repeating pattern. Like say instead of ABC we get ABA, then ABC. So these are stacking faults, and these are mainly can be seen in the closed packed structures of hexagonal closed packing and different types of other closed packings. Now, when we are going into the nano regime, when we are going into the nano regime, the same material uh, will have a simple single or symmetric twinning as well as five-fold symmetric twinning. So in Rajun regime, we can see that the material has single or multiple twinning, simple or sorry, not multiple, symmetric twinning, as well as five-fold symmetric twinning. Now, these different types of twinning patterns, they result into mm, a structure which is known as uh, decahedral and truncated decahedral nanostructures. Decahedral and truncated decahedral nanostructures below a critical size. Below a critical size, and the the nanotwins in it has been found that the nanotwins in nanocrystalline copper particles that are embedded in an amorphous, if these are embedded in an amorphous alloy, FeZrB alloy. Okay, so these defects can be seen. Now these nanotwins, they are actually called nanotwins. They are due to a strain developed in the copper amorphous interface. So there are nanotwins which are developed in when the copper particles are embedded in non-crystalline copper particles embedded in an alloy. Say it is FeZrB alloy, and this nanotwins are due to strains developed in the materials. Now these twins are mainly observed normally twins are mainly observed in crystals which are subject to a great deformation at a higher strain rate and at lower temperature. So usually a high strain rate as well as low temperature. In these two conditions, if these two conditions are met, we can expect a formation of twins. Now, during the crystallization of liquid metals, it is expected that the volume misfit strains can be easily accommodated in the liquid phase. So, talk about volume misfit strains during crystallization. It is expected that it is very much absorbed or accommodated in the liquid phase. Hence, one does not anticipate the formation of twins in the nucleating crystallites. So when the crystals is nucleating, that is, it is getting solidified from the molten state, there is less formation, there is less chance of formation of twins. Okay. Now, during the voids, now the nanocrystallites after formation, the formation of voids can form in the slides. These voids can may be situated either at the triple junction or as large porosities or as large porosities. Due to insufficient compaction and centering, and they arise these voids as mentioned here. These voids, they are formed mainly due to insufficient compaction, number one, and the second is centering, insufficient centering. If these two processes are not sufficient enough, there is very much possibility of formation of voids. Now, these are structurally more important than pores. Now, the triple junction voids, for in particular, arise as a result of relaxation of nanocrystalline grain boundaries. Do it in a different way. Triple junction voids they are arising triple junction voids. They are arising as a result of relaxation on X line grain 2. So when the nanocrystalline grain boundary is relaxed, there is formation of triple junction. Triple junction is where three junctions meet of different crystalline orientation. Triple junctions. Now the nanocrystalline, the substrate. Now the nanocrystalline, a fraction of the atoms lie in the interface. So assuming that so in nanocrystalline, some fraction of atoms they are at the interface. And assuming that the grains have a spherical shape, and the volume fraction of nanocrystalline materials associated with boundaries is estimated to be Vi is equal to 3 delta by D, where delta is the average interface thickness and D is the average grain diameter. The average interface thickness and the small d is the grain diameter. So this is the equation. So what we can observe or we can infer from these equations is if the volume fraction of the interface is 60%, then the grains or the D, they have got a size of 5 nanometers. Number one. Number two, if it goes down by 30%, we have grains which are larger, 10 nanometer, and for 3% 3% volume fraction, the grain size is around 100 nanometers. And we assume that this is 1 nanometer here. This is our assumption. Now this volume fraction is very much important to determining the phase property, phase mixture model, according to which according to which any physical property is equal to the volume fraction of the crystal into the property itself plus volume fraction of the interface into the property of the interface itself. So the intercrystalline components which include the green boundaries, triple junctions and quadratic dipoles. So the intercrystalline components they contribute. So we take a cubic unit cell or a regular polyhedron unit cell of nanocrystalline materials. The volume fraction of each of the component can be expressed is d minus d cube by d cube for the crystal, and for the grain boundaries, the volume fraction of the grain boundaries, it is around 6 into d minus delta whole cube into delta by 2 divided by d cube.